Hi everyone, my name is Andreas Hinterreiter. I'm a PhD student at Johannes Kepler University Linz. I'm a member of the Visual Data Science group at the Institute of Computer Graphics there. And as part of my PhD, I've spent the last year at the Biomedical Image Analysis group at Imperial College London. And during my stay there, Bernhard Kainz asked me to give a guest lecture about visualization. And this year he asked me to record it. So in this lecture I will talk a little bit about the different tasks that visualizations can be used for and how these tasks relate to the different techniques that visualization researchers have come up with. In healthcare and the medical sciences, just like in almost any other field, more and more data is being created and is made available for people to use. And the same development that has led to the increased importance of machine learning in these fields has also led people to realize the potentials of data visualization. Especially in healthcare, data visualization is of increasing importance because it cares about the human in the loop. I'd like to start with a short introduction about what visualization is and why it is a nice tool to have in your toolbox. In her book on visualization, Tamara Munzner writes that visualization systems provide visual representations of datasets designed to help people carry out tasks more effectively. And as you can see, I've highlighted a couple of words here. First of all, as the name already says, visualizations are visual. And this is important because the human brain is very good at processing visual information both effectively and efficiently. Second, I've highlighted the word datasets to stress that, just like machine learning, visualization can always only be as good as the data you have. Third, I've highlighted people because, as I already mentioned, visualization very much cares about the human in the loop. And finally, I've highlighted tasks because in my opinion, it's very important when you create a visualization to think about the tasks that it will be used for. And I will talk about those tasks in more detail later on. I'd now like to discuss 3 examples that should give you an idea of the different powers of visualization. In this table here you can see Anscombe's quartet. This is a collection of 4 datasets, pairs of x and y values, that were designed to all have exactly the same mean of x, the same variance in x direction, the same mean of y, same variance of y. They even have the same correlation coefficient, the same regression line to a couple of decimal places, and the same r-squared value. So the descriptive statistics that you can see on the right here, they give you no chance to distinguish between those datasets. But as soon as you look at scatter plots of those datasets, you immediately see how different they are. The first one looks more like you'd expect a dataset with some linear correlation to look like. The second is more like a power law. And then you have these other datasets with outliers. In fact, you can even construct your own Anscombe's quartet-like dataset that looks any way you want and still has the same descriptive statistics. If you want, you can even make it look like this data dinosaur here. And again, this shows how quickly, using visualizations, you can get more insights about datasets than simply looking at some numbers. In this next example, I want to talk a little bit about the work of John Snow. I'm not kidding, that's actually this guy's name. John Snow was an epidemiologist in London, and at the time he practiced, there was a really bad cholera outbreak in the city. And no one really knew how it spread and what caused the disease. So what John Snow did, he took a map of London, and for each recorded cholera death, he made a little mark in the map. Then he also made marks for all the water pumps in the region. And what he found was that almost all the cholera deaths concentrated around one specific water pump. And with this evidence, he got the authorities to check out this pump in more detail. They actually found the bacteria there that caused cholera, and they closed down the water pump. And this actually caused the outbreak to settle. And in this example, you can see the real-life impact that insights gained by visualizations can have, in this case, for example, on the health of people. For this next example, I want to talk about the work of Charles Joseph Minard, who was a French civil engineer in the 19th century, and he is the inventor of the infographic. And he created a visualization that Edward Tufte, who is probably the most renowned visualization expert today, called the best statistical graph ever created. This is the original version, and I will just switch to one with a little higher resolution. And this is a visualization that Charles-Joseph Minard created for Napoleon's Russia campaign in 1812. You can see a map with the border between Poland and Russia on the left and Moscow on the right. And this beige band here stands for the number of people in the army. You can see that with each battle, the number of people gets smaller and smaller as more and more people die. And even on the way back, you can see that how many people die even just crossing this river here. And he combined this graphic with a timeline of the temperatures in Russia. You can see that, for example, here, when they crossed the river and many people died, that it was minus 20 degrees Celsius. And this infographic caused many people to realize just how catastrophic this Russia campaign was and how many people died, how few made it back, which you can see all the way here at the left. And this is a perfect example of how you can use visualization as a powerful tool for storytelling. So with these examples, I've tried to show you a little bit how visualizations can get the point across more effectively than raw data, as we saw with Anscombe's quartet. How the insights gained with visualizations can have real-world relevance, as was the case in Jon Snow's cholera example. And finally, that visualization can be a very powerful tool for storytelling, as we saw in Minard's infographic. And I will later hopefully be able to show that visualization can even help people to answer questions that they don't even know yet how to ask. But all of this can only be done if they are well designed. So in the next part of my lecture, I will talk a little bit about how you can approach the design of visualizations. So to approach the design of visualizations in a more structured way, researchers have come up with different categorizations or abstractions, and one deals with what can be visualized. So it's about the different data types. What you most have when you create visualizations is tabular data. In a table, there are different items that are the rows, and each item has some associated data attributes in the columns, and each cell contains a single the single value for an attribute. The concept of tabular data can also be extended to multiple dimensions, of course. A fundamentally different kind of data is network data. In a network, you have nodes and that are joined by links. One example would be a social network where the nodes are people and the links are the relationships between people. Or in a computer network, for example, where the nodes are the computers and the links are the connections between computers. You can even have data associated with the links, for example, the amount of data that flows on a given connection. Then there are also fields, and in my opinion, fields are like a special kind of tabular data, where some of the attributes are spatial positions. An example of fields are vector fields in physics, or temperature field would also be an example. And finally, we have geometry data. So this is data where you have some shape that has data on top. Like the best example for this kind of data is geographical data, where the shapes would be countries, and you have some data like GDP or birth rate on top of these geographical regions. Usually each specific visualization technique works well for one or exactly one type of data. So when you start developing your visualization, it makes sense to think about your data in an abstract way. So far I've talked only about the structure of the data and not really about the individual values here. And also these values can be of different types. So there are different types of attributes. Categorical ones, for example, a type of fruit would be a categorical one. It can be either apple, banana, whatever. There are ordered ones, like a nice example is t-shirt sizes, like small, medium, large. They are not numeric, but they still have an inherent order to them. And finally, what you very often have is just quantitative data. So these are values that can be represented by a single number. Also, the ordering direction of the data can be different. You can have sequential data that starts at some point and then goes all the way up to infinity. For example, an absolute temperature scale would be sequential. Very often you have diverging data. This means that also negative values are allowed. And sometimes, especially in the case when you deal with something that's related to circular movements or angles, you have a cyclic ordering direction. Another thing that makes a big difference when you create your visualization is the dataset availability. Datasets can be static, so they will not change during the visualization, or they can be dynamic, and of course this makes a very big difference how you have to design your visualization. Now that we've talked about what can be visualized, we can ask the question why we want to create a visualization. And also to answer this question, people have come up with abstracted categories, more or less, of different user tasks. So the tasks that people will perform when they work with your visualization. And one example of an action-based task is search, which can be further subdivided into different tasks, like when you know what you're searching for or whether you don't know what you're searching for. Those tasks can be look up, browse, locate. One task that I've highlighted here because it is a very important one, especially in interactive visualizations, is explore. So this is a task that people perform when they don't know what they're looking for, they don't know where they're looking for it, but they still want to create some sort of insight or intuition about the data. There are also more high-level tasks, like do you want to use your visualization to actually analyze something, to discover insights? Do you use a visualization to present insights that you already found earlier or that someone else already found earlier? And one simple task is also just to enjoy some nice visualizations. And as an example of different tasks, back when I created these slides in November last year, people talked a lot about Game of Thrones because this was shortly after season 8. And I've still left this in because it's, I think, quite a nice example. This visualization shows all the different characters in season 3 in a node link diagram, where the links are episodes or scenes where characters appear together. And this graph enables, or this visualization enables a couple of different tasks. You can look for specific relationships that you already know, or you can locate a certain character and just browse through all the relationships with other characters. But it can also be used to communicate, for example, especially when you pair it with another visualization that shows season 8. Maybe you can use this to tell your friend why season 8 sucked. In a bit more detail, we can ask ourselves the questions what the targets of these tasks are. So what do people actually want to do when they perform this broad analyze task, for example? They might want to find trends or outliers or certain other not so well-defined features of datasets. They can target either a single attribute with their analysis or multiple ones at the same times. They can try to find dependencies between multiple attributes, correlations, or similarities. When they only look at a single attribute, they might be interested in the distribution of the values or in finding extreme values. And again, each visualization technique is differently well suited to enable these more detailed user tasks. Now, This is true mostly for numerical attributes. For network data, tasks, just as we saw in the Game of Thrones example, would be to explore, analyze the topology or different paths through the network. Finally, for spatial data, a typical task would be to analyze the shape of an object that results from your spatial data. Now that we've talked about the what of visualization, which was the data, and the why of visualization, which was the user tasks, we can finally talk about the how, and this leads us to marks. Marks are the atomic pieces that make up a visualization, and together with other components like axis ticks, they convey the actual data. And in the simplest cases, marks are simply items like points, lines, or areas. But as we saw in the graph example, they can also be connections between items or containments of other items. Each mark has several visual channels, and each of these channels has a different effectivity when it comes to conveying different types of data. Here you can see a scale from least at the bottom to most effective at the top. And for ordered attributes, or numerical attributes, there are magnitude channels that work very well. The best one to use is position on a common scale. You can also use unaligned scales, but they don't work quite as well. The length channel of a mark also works really well for ordered attributes. And for me, surprisingly, the tilt channel also works pretty well. With area, you should be a bit more careful, because this is a bit tricky to see the difference. Then there are also less suitable channels, like the depth position in a 3D plot, or the color channels of luminance and saturation. Now, you should really be careful when you use luminance and saturation, because people can only distinguish a couple of these at once. Then only in extreme cases you should use curvature and the volume in 3D plots to convey ordered attributes. For categorical attributes, we have different channels. One would be spatial region. So, for example, where in your plot does a mark show up? Of course, this should not collide with the position for a magnitude. We have the color hue that works pretty well for conveying categorical attributes. I don't see this a lot, but motion turns out to be quite nice for categorical attributes, especially because people can quickly spot when something moves. And something that's used a lot, but that is actually not quite at the top of the scale of effectivity, is the shape channel. And again, this is because it gets tricky to quickly distinguish between shapes when you use more than, let's say, 4 or 5 different shapes at once. Now we basically have everything that we need to talk about established visualization techniques. So I will talk about how different marks with their channels are used to visualize certain types of data and to enable different types of user tasks. And I will start with some very simple visualizations that you all know, because I want to give you an idea of how you think about these visualizations in a more abstract way in terms of tasks, channels, and marks. For tabular data, one of the most widely used visualization techniques is the scatter plot. In the scatter plot, you typically have 2 quantitative attributes that are encoded in the x and y positions of the marks. Each mark stands for 1 data item. And the tasks that a scatter plot enables are finding trends, outliers, distribution of values, correlation between attributes, and you can also identify clusters. We should also think about how well our visualizations scale with the number of data items in our dataset, and the scatter plot typically change to hundreds of items. In some cases, I've also seen some that work really well still with thousands of items. Again, for tabular data, we have bar charts. In a bar chart, there is only 1 quantitative value, which is encoded in the bar height. And there's one categorical key attribute that is encoded along the x-axis. So each bar stands for one category. Bar charts support lookup and comparison tasks very well, but they scale not as nicely as scatter plots, only to a couple of dozens to hundreds of different categories. Of course, with the magnitude channel they scale very well. Then still for tabular data we have dot charts or line charts. So those are very similar to bar charts, just that now the bar is replaced by a dot, and perhaps you can join these dots with a line. This only works when the categorical attribute is now an ordered key attribute, like in these examples here, where somebody weighed their cat every year and recorded the weight. The year is an ordered key attribute. And these charts work very well for showing trends. And they scale to hundreds of different levels, and now also for the key attribute. Finally, another visualization technique for tabular data is the heat map. In a heat map we have either one or two categorical key attributes that are aligned along the axis of this heat map. We have an additional numeric attribute, quantitative value, that is encoded in the color. Heat maps work very well for letting users find clusters or outliers. You can spot a particularly dark cell very quickly and look up the corresponding attributes. They allow identifying trends, and they often serve as very nice summaries of large data sets. If you make the actual cells very small, which you can sometimes do quite nicely, they scale to millions of items with hundreds of categorical attributes. But as I mentioned earlier, since we use the color channel for the numerical attribute, this is a bit tricky because we can only distinguish about 3 to 11, maybe 12 different shades of color. So there you have to be careful about the resolution of the numerical attribute. Just an example of how heat maps can be used in certain situations where other types of charts would cause too much visual clutter. I've picked confusion flow. This is a visualization for the temporal development of class confusions of classification models during learning. This is a work that I've recently published in TVCG, and if you're interested you can check it out. You can try the online prototype under the link down at the bottom. There are also many other visualization techniques for tabular data, like stack bar charts, pie and donut charts, which are, well, many people in the visualization community really dislike them. And there are many other ones. If you want to find out more, you can go to the Data Viz catalog under this link at the bottom. And it's a very nice summary of all the different techniques and in which scenarios it's a good idea or a bad idea to use them. Then when it comes to spatial data, I've picked chloroplath maps as an example. Here we have geographic geometry data, and we have kind of a table where each region has a certain quantitative attribute assigned to it. The space is used to convey the shapes of the geographic data, and the numerical attribute is encoded in the color of the regions. And one task that is supported by chloroplath maps is to find correlation, like is there a difference between north and south in the numerical attributes, but also to find outliers if you can find one country that is particularly dark, for example. This scales to a couple of hundred spatial regions, especially when you add interactions like zooming and panning. It scales even better. And just like in the heat map, since we're using color for the numerical attribute, you You have to be careful because we can only distinguish between 3 and 11, maybe 12 different levels. For spatial data, again, there is much more. You can have all sorts of vector field visualizations, rendering with transfer functions, contour plots which make use of isocontour lines, and I can't go into details. I just selected a couple of examples from real papers here. Finally, we already saw an example of a node link layout. This is a kind of visualization technique that's used for network and tree data. A point mark is used for each node. The connection marks are lines that connect the nodes. And as we already heard earlier, typical tasks for network and tree data are exploring topologies and locating paths. The thing with node link diagrams is that they don't scale particularly well. You can only usually have a couple of dozens, maybe hundreds of nodes, a couple of hundreds of links, and at some point things start to clutter a lot. This is why people came up with many more different ways of visualizing network and tree data. And for this kind of data, I just want to refer you to a really nice website about multivariate network visualization. They have a nice wizard where you can input certain things that you know about your dataset, and then it recommends which visualization techniques work well and which not so well. Now, on top of all these visualization techniques, we have what is called cross-cutting techniques. And there are two very important ones. One is interaction. And this allows users to manipulate the visualizations on demand. And just like the visualization techniques themselves, these cross-cutting techniques again enable a whole lot of different tasks that you can think about in a slightly abstracted way. A simple type of it falls under the category of interaction, but it's not really that interactive, is if you just have a visualization that changes over time by itself. Then a very useful one is selection, which enables, for example, to find details about specific data points. Navigation, I already mentioned this in the chloroplath maps. This allows zooming, panning, constraining your visualization to a certain region. And you can also have users of your visualization work with the data in a special way, like slicing the data, cutting out certain parts, projecting the attributes to a new coordinate system. Another cross-cutting technique that can be used in conjunction with interaction is multiple views. And this is very useful because we saw that each visualization has its own strength, and sometimes it's great to combine different visualizations, either of the same or of different data that are linked across multiple views, just to combine the different strengths of the techniques. And one way to do this is to juxtapose, so simply place two visualizations side by side. Again, in the best case they are linked, so whatever you do in one visualization is in some way also performed in the other one. And as I said, they can share the data or use different data. And of course, the navigation, so the interaction that you use on one can be the same in both views. You don't have to place these visualizations side by side. In many cases, you can actually superimpose them and just place two plots on top of each other. Visualization researchers have also tried to think about how to tell when a visualization is good and when it's bad. And along with this, these evaluation criteria, I also want to give you some rules of thumb for creating visualizations that work well. First of all, when you want to evaluate if a visualization works well, there are 4 levels of design. And on each of these levels, something can go wrong or right. First of all, you have to understand why you create the visualization. So you have to understand the needs for the visualization, especially when you create the visualization for somebody else to use. Then, when you already know why you create the visualization, the next thing where something can go wrong is that you show the wrong thing. Then, even if you've selected the right thing to show, you can show it in the wrong way. so you may select the right or the wrong visual encoding. And of course also interaction techniques. And finally, even if you made all the choices correctly and you actually create the visualization, things can still go wrong in the algorithm side. If something is too slow, that especially in interactive visualizations, people have to wait ages for something to show. Now I want to give you some rules of thumb. No unjustified 3D. This is like a mantra in the visualization community. As an example, I have here this 3D bar chart. And I don't know if somebody of you can see what the actual data shows, but here there's a lot of occlusion and discrepancies in the appearance of the heights of the bars. If you look at a different kind of visualization, a simple heat map that shows the data from the top, you can see that this is actually supposed to be a question mark, which is almost impossible to see, in my opinion, in this 3D bar chart. But also you should use 3D when you really need it, so do not create unjustified 2D visualizations just because you think 3D is always bad. Then, in my opinion, one of the most important rules is resolution over immersion, especially in scientific contexts. This means that all the space that your visualization takes up, or as much of the space as possible, should be devoted to actually showing the data. You should not use what Edward Tufte called chart chunk just to create some immersion. This usually hides what you really want to show about your data. Chart chunk is also related to things like, well, I have a hard time even naming these things that people used here, like this weird filling of these 3D shaped bars and the unnecessary 3D. In the first place, the weird legend that they use the background color. All things like these are chart chunk, and you have to think about this. If you remove all of this, you will automatically increase the density of data, and what Edward Tufte called data to ink ratio. You should also think about getting things right in black and white. This used to be more important when people printed things out, but it still helps, even if just to prevent yourself from using colors in too crazy ways. Then this is important when it comes to interactive visualization, eye speed memory. So you should, if possible, never rely on the user of your visualization to memorize things. It's always best if they can see things. So if they want to compare two values, these values at best should be visible at the same time. Then again, something mostly for interactive visualizations, but it also can be relevant if you show static ones in a given sequence. You should always provide an overview first and then provide details on demand. Again, in case of interactive visualizations, they must be responsive, because otherwise they are horrible to use. And a very nice summary of all of these rules. Always think about the function, about the user tasks first, and then about the form. Just one example of what not to do, this 2018 salary bar chart, where the numbers, when you look at the large numbers and the bars, it makes absolutely no sense. I think I figured out that what they actually used for the bars is the number of home runs, even though they said they visualize the salary of the home run hitters. More crazy examples and quite funny examples can be found at vis.wtf. Bernhard also asked me to talk a little bit about unstructured data. So far, everything that I've talked about in the data abstraction section and in the section under visualization techniques dealt with structured data. Tabular data, network data, fields, and geometry data is all nicely structured. But what about text and images? And it turns out that this unstructured data is hugely important. It is estimated that about 70 to 80% of all the data in companies is unstructured. In the medical sciences, unstructured data would be imaging data, for example, or textual reports. Unfortunately, I can only tell you to structure your data. So you somehow need some process of converting your unstructured data to structured data to use visualization techniques and other statistical techniques, obviously. For textual data, this can be as simple as counting your words. So if you count the words and assign a word frequency to each word, you can plot a point cloud. The size of each word correlates with the word frequency. In more complicated cases, of course, you can use things like natural language processing for text data, feature extractors for images. Something that is always nice in this context is dimensionality reduction. I will talk about this next. In any case, you need to convert your unstructured data to some form that allows you to calculate distances or to otherwise end up with some numerical or categorical attributes. I just mentioned that one nice tool to have is dimensionality reduction when you deal with the result of structuring your unstructured data. And this is because this result is often a high-dimensional representation of your dataset. And in order to create two-dimensional visualizations or three-dimensional ones, you need to somehow reduce the dimensionality of this representation. One classic way to do so, that you probably all know, is principal component analysis. And here you basically combine the original axis in such a way that the first new of the combined axis has the greatest variance along it. The second component has the second greatest, and so on. And then if you simply drop all but the first n components, you've reduced your datasets to n dimensions. And the idea is that since the later components have lower variance, you don't lose much information. This kind of works for the MNIST dataset of handwritten digits. You can see that some of the classes are separated in this PCA representation, but even this simple image dataset seems to be too complicated to get a nice representation by just looking at the variance. So one other way is to look at pairwise distances, and this is done, for example, in multidimensional scaling, or MDS. The way this works is that you construct a dissimilarity matrix, so simply the matrix of pairwise distances of your data points, and then you try to find the configuration of low-dimensional points that best matches this dissimilarity matrix. This kind of works, as we can see here for some of the MNIST classes. It really separates them nicely into clusters. But this is hugely computationally expensive because you don't only have to calculate the distance matrix for the high-dimensional data set, but you have to calculate it over and over again when you try to find the low-dimensional representation. Another conceptually similar approach is isomap, but here you do not use the immediate distances between the high-dimensional data points, but you construct a neighborhood graph and then you use the graph distances. So something, for example, would have distance 1 if it's a direct neighbor of another point, distance 2 if it's a second nearest neighbor. These so-called geodesic distances create also nice plots. For example, again for the MNIST dataset, the clusters separate even more nicely. There are even better ways and more modern ways to do similar things. TSNE and UMAP. So TSNE stands for T-distributed stochastic neighborhood embedding. UMAP stands for uniform manifold approximation and projection. And here the idea is very similar. You basically look at pairwise data points, but you only look at data points in a certain neighborhood of your point. So again, you construct something like a neighborhood graph. Then you use this graph to greatly reduce the number of distances that you have to calculate. Then you also apply a number of tricks. You treat those distances not directly, but you convert them into joint probability distributions. Then you try to find again low-dimensional representations that have similar joint probabilities of neighborhood between these points. And these two techniques have been used a lot recently. They work pretty well for even very high dimensional datasets. You can see here in this representation of the MNIST dataset that now really all the clusters are separated nicely. And even within these clusters, local information is preserved very well, which means that one side of a cluster has a certain type of ones, for example, here on the top. These are slanted in one way. The other side of the cluster has the ones slanted the other way. Here a quick comparison of using these different techniques that shows you that in terms of clustering, things like TSNE or UMAP work much better than the older techniques of PCA and ISOMAP, but they also have their strengths. Now I'd like to use a practical example to show you how you can combine dimensionality reduction with initially unstructured data and also visual marks and their different channels to create really cool visualizations. And in this case I'd like to talk about the visualization idiom of time curves. So time curves start from a timeline, so a simple temporal sequence of unstructured data items. In the examples that I will show here, these are the states that Wikipedia articles are in. You simply have a temporal record of the states. And then just by defining a similarity metric on these states, for example an edit distance, you can fold the linear timeline into a time curve and you can show pretty cool things. Here, for example, you can see the edit history of the Wikipedia article on chocolate visualized as a time curve. Now each point mark stands for one state of the article, and the point marks are joined in order of their temporal sequence, but they are placed according to their similarity. This gives rise to nice patterns, like for example between these blue points. You can see that there was what is called an edit war, where people always undid edits of the other editor. So the article ended up to go from one state to one that was similar to the one before, and then back and forth and back and forth. And these kind of patterns show up nicely in time curves. In our work, we used a similar concept to visualize differences and similarities in solution algorithms for the Rubik's Cube. So the principle is the same. We find some way of structuring the Rubik's Cube into a feature vector. We define a similarity metric, then we can plot the temporal sequence but position the points according to the similarity. And this creates really nice plots that show differences and similarities when you combine time curves for many randomly initialized cubes. We also have a really nice interactive prototype that you can check out if you want to see how something like this then looks in an almost finished product. So this thing, it already works great, it has a lot of features, it's continually expanded. And if you want to check it out, just go to this link down there and try some of the interactions. It should give you an idea of how a complex visualization system developed by these researchers can look like. Now I'd like to talk a little bit about some tools for creating visualizations and also interactive visualizations. If you're using Python, you've definitely used at some point matplotlib. It's really nice for creating static visualizations directly in your Jupyter Notebook, for example. There's also Seaborn, which has some additional nice functionality for statistical data visualization. And of course, many other programming languages like MATLAB, R, or Mathematica have all sorts of built-in functionality for creating static visualizations. If you want to create more complex dashboard-like visualizations, there is Tableau, which is basically the leader for business intelligence visualization solutions. There's also Microsoft Power BI, but I think both of these tools are not really suitable for creating simple small visualizations. They are more for like full-blown dashboards with lots of complex interactions. For creating simple interactive visualizations, I can recommend Vega and Vega Lite in JavaScript, so for browser-based applications. For Vega and Vega Lite, the creators tried to abstract different concepts, similar to what I talked about in the data and task abstraction, into simple commands that you can piece together to create pretty nice interactive visualizations. There's also an API based on Vega Lite for Python called Altair. This is really nice if you want to create simple interactive visualizations directly from your Jupyter Notebook. What we mostly use for the more complex visualizations for browser-based applications is D3. This is a JavaScript library that gives you full control over drawing all sorts of SVG elements. So it gives you full control, as I said, and this is what is necessary if you want to create custom solutions. If you're interested in learning more about visualization, the book on the left here, Visualization Analysis and Design by Tamara Munzner, is the book that I've used as a basis for the data and task abstraction sections of this lecture. It's a really nice textbook if you're interested more in the technical and conceptual aspects of visualization. But I can also highly recommend all the books by Edward Tufte. He has authored 4 books about visualization. They are all beautifully made. This one, The Visual Display of Quantitative Information, is the first one, and it's a really nice introduction with nice examples and also written very well. So to summarize this lecture, I hope I could show you that well-designed visualizations address specific tasks. There are many existing and well-established visualization idioms for the most commonly used tasks, especially on structured data. For unstructured data, you need to structure them first, which is often followed by dimensionality reductions. And finally, and most importantly, visualizations are powerful tools for creating insights and for telling stories in a compelling way. If you have any questions, you can either let Bernhard Kainz know, I'm sure he will forward them to me, or just contact me directly under my Imperial or JKU email addresses. Thanks for listening.